So is my screen visible to all of you? Is my audio audible? My screen is visible, right? Okay, nice. Okay, so welcome all of you to the week third discussion of this course, Social Networks, and this course was taken originally by Professor Sudarshan Iyengar, Professor and Head of the Department of Computer Science and Engineering of IIT Ropar. Myself, Ayan Paul, I'm a PMRF Research Scholar from IIT Kharagpur, and I'm a TA of this course. By TA, my duties are I have to solve a few questions that will be very much similar to your assignment, so that whenever you will solve your assignment, you will not feel it's completely new. Okay, so it will be familiar to you and you can score better in your assignments. That is my duty. But before that, what I prefer is always to discuss some of the theories of that we have covered in this week, so that it will be easier for us to solve the assignment question. Okay, so with that, let's start the discussion. Okay, yeah. So this week we will learn about strength of weak ties. Okay, so strength of weak ties. So there are two type of ties. One is strong tie and one is weak tie. Okay, so what is this weak tie or strength of weak tie? So strength of weak tie means weak social connection. Okay, so weak social connection means acquaintances, means person that you know, not your friend but person that you know, are often more powerful than strong connection, that is close friends, for spreading new information and opportunity. So again I am repeating, what we are talking about is strength of weak ties. What is weak ties? Weak ties means weak social connection. Ties means in common terms, you can compare ties with friendship. Okay, so weak friendship, so weak ties, so weak social connection. That means acquaintances means person that you know, that they might not be your close friends but you just know. Okay, so that is known as weak tie, weak social connection, or you can also tell as acquaintances, are more often powerful than strong connection, that is close friends, for spreading new information and opportunities. Okay, so this is the strength of weak tie. A weak tie is a social connection characterized by low interaction frequency, low emotional closeness, low trust, and low neighborhood overlap. Okay, so these are some of the characteristics of weak ties. Example can be your college acquaintances, friends of friends, not your friend but your friends of friends. Okay, distant colleague or LinkedIn contacts. So these are some of the examples of weak ties. Okay, so this is known as strength of weak ties. That means information, they are your weak ties are often more powerful than strong ties in spreading new information and opportunity. So that is known as strength of weak ties. Okay, so this is the topic. Now where we have got this from, this concept has been first given by Granovetter in his experiment known as Granovetter's experiment, the strength of weak ties. Okay, so that is given by Granovetter. Full name is Mark Granovetter, in the year 1973. Okay, in the paper The Strength of Weak Ties in the Field Sociology and Social Network Analysis. Okay, so what has been the objective of his paper or objective of his experiment is to test how people actually find jobs and whether strong ties or weak ties are more important in providing new job opportunities or new job information. Okay, so that is the objective of the experiment. So methodology that Granovetter has adopted is he has taken 282 participants or 282 job changer in Boston area of USA. Okay, and he asked the key question that how did you find your current job. So they were asked who told them about the job, how close was the person to them. Okay, so this is the experiment that Granovetter has done. Again, I am repeating that Mark Granovetter in the year 1973, he performed a social experiment known as the strength of weak ties. So what was the objective? Objective is to test how people actually find jobs and whether strong ties or weak ties are more important in providing the new job information or new job opportunity. Okay, so this is the thing. So for that he questioned 282 participants or job changes in the Boston area of USA. And key question that he asked is how did you find your current job, and they were asked about who told them about the job and how close was the person to them. Okay, so this was the experiment and the result. Okay, so before that, what is strong ties and weak ties according to that experiment? So strong ties is close friends, family and frequent interaction. Okay, so that are strong ties. And weak ties, acquaintances, occasional contacts, former classmates and distant colleagues. Okay, these are the weak ties according to Granovetter. Okay, and the key finding or the main result that he found from the experiment is that 56% or approximately 56% got jobs through weak ties and only approximately 17% through strong ties. So that means most people found jobs through weak ties, not strong ties. Okay, so why weak ties are more important? Reason being behind that is that strong ties belong to the same social circle. Okay, that means whatever you will discuss in your same social circle, that is a redundant information. Okay, so that means you and your close friend, whatever you will discuss again and again, that is redundant information. You might know the same information that your close friend might know, but whenever we are talking about weak ties, they belong to different social circles. So as your circle is different, you might have different information or you have novel information. Okay, so this is the thing. Hence weak ties act as bridge between the communities. Okay, so this is the thing. So conclusion of this Granovetter experiment is weak ties play a crucial role in information diffusion, opportunity discovery and social mobility. So this becomes the famous strength of weak ties theory. Okay, so this is done by Granovetter in the year 1973. Okay, so this is the strength of weak ties concept in your social network that we will be discussing today, or that is the basis of discussion for our today. Okay, so is the experiment clear to all of you? Any questions on this? Okay, nice. So let's move forward and discuss the next topic, that is triads and
Is this important for exams, sir?
yeah, sure. This is the basis of your strength of weak ties. So at least you should know the theory or know the experiment. Okay, like who has done this strength of weak ties theory? Short question, like in which place it has been taken place, number of participants, what was the result. So yeah, simple information you should keep in mind. A very small question might come,
Okay, sir.
might not come also, but might come. So it is the basis for this. So I hope you will keep this in mind. Okay, so let's move forward.
Okay, sir.
So triads and triadiac closure. So what is a triad? That is again an important thing. A triad is a group of three nodes A, B, C, and the edges connection among them in a social network. So any three nodes like this A, like if I tell this A, B, and C, this is will form a triad. Okay, A, B, C will form a triad. So triads are basic building block of social structure and are used to study social balance, transformation, transitivity, and community structure. So forget this. So there can be open open triad and closed triad. So let me erase this, already have this. Yeah, open triad and closed triad. What is an open triad? This on the right, on the left hand side, this is known as triad. So three, A, B, and C. Okay, so this is a open triad. That means A is connected to B and A is connected to C, but B is not connected to C. That is known as open triad. Okay, so only two edges present. A is connected to B, and let's say B is connected to C, or you can say A is connected to B, A is connected to C, but B is not connected to C. That is known as open triad. But there is another triad known as closed triad. All three edges present, A, B, B, C, and AC, forms a triangle. So this is known as closed triad. This phenomena is known as triadiac closure. Okay, so triadiac closure is the principle. Okay, someone is joining. Okay. So this phenomenon is only called as triadiac closure. So triadiac closure, if A is connected to B and B is connected to C, A is more likely to become connected to C. So this phenomena is known as triadiac closure. So this explains why friends of friends tend to become friends. So definitely, like A is a friend of B and B is a friend of A is a friend of C, then there is a strong chance that B is also a friend of C. Okay, so that is known as triadiac closure. Significance: it increases trust, promotes community formation. So by this only your community can build. Like this triadiac closure 3333 triadiac closure. If you keep on forming this, you will end up with a community. So increased clustering, explain network densification. Probabilistic interpretation: A, B, and BC exist, then probability of AC forming is high. So that is known as triadiac closure phenomena. Okay, so this is very simple. Again, I am telling triad. Any three friends like A, B, C will form a triad. Okay. Now, what will happen is generally there is open triad. Like A is connected to B and A is connected to C. Okay, so what about if B is connected to C? If B is connected to C, then that is known as closed triad, and this phenomena of forming a closed triad is known as triadiac closure. Okay, so A is connected to B, A is connected to C, so there is strong chance that B is also connected to C. Okay, so that is known as triadiac closure. So this is again a very simple concept, but it is important. Okay, so this is triads and triadiac closure. Now we just talk about clustering coefficient. So it measures how close a node's neighbor are to being a complete click or fully connected. Okay, so you can see this can be you let's say let me tell this as Z. If Z can form nodes with A, B, C, D, E, and E. Okay, so this is Z. But if all the edges or all the nodes are connected or not, so that is a measure, that is a measure of clustering coefficient. So it measures how a close and nodes neighbor are being complete click. Okay, so this over here is a complete click, means all the nodes are connected to each other. Okay, A is connected to B, A is connected to Z, A is connected to C, A is connected to D, A is connected to E. Similarly, all the nodes are connected to each other. So that means this form a click or a complete click. Okay, but there can be this there can be this the fraction of possible connection among a nodes neighbor that actually exists. So there can be a case where not all nodes are connected to each other. So that is known as that is known as that is known that it's not a complete clique but a partial connection. Okay, so that is clustering coefficient. So the formula, this is the formula of clustering coefficient, ci 2ei ki minus 1. Okay, ki means the degree of node I, that means node I is connected to how many nodes, and ei number of edges among the neighbors of I. So this is the formula of clustering coefficient. Okay, so here you can see this is clustering coefficient is 1 if all the neighbors are interconnected, that is complete clique. Ci equals to 0 if none of the neighbors are connected. So that is that is known as there is no clique formation or zero clique formation. So that is clustering coefficient here is 0. So again I am repeating, clustering coefficient, it measures how close a node's neighbor are being a complete clique, that is fully connected. Okay, so node, let's say node is your z. Okay, so node is your z. So we have to see all the neighbors of z. What are the neighbors of z? A, B, C, D, E. If all the neighbors are fully connected, then we can say that the clustering coefficient is 1. Okay, if the neighbors are not connected, like z is connected to A, B, C, D, E, but A, B, C, D, E are together not connected at all, so that is why we can say that clustering coefficient here is 0. Okay, and this is the formula, that is 2 into ei. 2 into ei is number of edges among the neighbors of I, and ki into ki minus 1. Ki is the degree of node I. So this is the formula of clustering coefficient. Okay, so this is the thing. Example also you can see, if a node A has 4 neighbors, then what are the maximum maximum possible links? 4 into 3 by 2. Okay, that is 4c 2. Okay, so that is how you will compute the you can say numerator. Okay, and denominator, actual links among them is 3. Okay, so 4 neighbors, maximum possible link is 6, but actual links among them is 3. So how we will calculate? 2 into 3, that is 2 ei divided by 4 into 3. Okay, so 4 is 4 because 4 neighbors, so there will be 4 degree of I, so that is why 4 into 3. So your answer will be 0.5. Or you can see over here this diagram, total possible number of friendship, that is 5 into 4 by 2, because that is again 5c2, that is why 5 into 4 by 2. Okay, so that will be from your denominator, and numerator is the total numerator is the total possible connection, so that is 6. Okay, so by that you can compute the clustering coefficient. So you can just remember this formula, 2ei ki by ki minus 1. Okay, what is ki? If 4 neighbors are there, so 4 into 4 minus 1. And what is ei? The actual number, actual links among them. Okay, 2 into ei, that is degree. Okay, so 2 into 3 divided by 4 into 3. Okay, so that will give you 0.5 as your answer. So that is how you will find out the clustering coefficient. Okay, very easy, but just remember this formula. So that is about clustering coefficient. Now neighborhood of node I denoted by ni is the set of all nodes directly connected to I. Okay, so ni that is j I e belongs to E. So E is the set as set of the network. So all the neighborhood of node I, all the edges that are connected, or all the nodes that are connected to your I is known as your neighbor of I. Okay, so that is how you can say. J is nothing but all the other nodes apart from I. So that is how you can calculate the neighborhood of I, node I. So that is neighborhood. Now let's this is important, that is the neighborhood overlap. So it is used to measure tie strength, embeddedness, and detect the local bridge. So neighborhood overlap definition: neighborhood overlap between I and J measures how many common neighbors they share relative to their total neighbors. Okay, so this is the formula of this neighborhood overlap. We write it as OIJ. So NI intersection nj, that means common neighbors between I and J, and then ni union nj minus 2. Okay, so that is how we can say, or you can say by this ni intersection nj, that is the common neighbor. K is nothing but degree of node I, kj is nothing but degree of node j, and minus ni this common neighbors. Okay, so ni intersection nz. So this is the good formula, you can just learn it. Ni intersection nj divided by k minus 1 plus kj minus 1 minus this common neighbor. Okay, so this is the formula. Okay, so you can see in very common term, that is common friends divided by total number of friends. Okay, that will give you the neighborhood overlap. Okay, so interpretation of this, if the overlap value is 0, so that means no mutual friends, or local bridge or weak tie. Low, that is weak tie, and high, that is strong tie or high embeddedness. Okay, so we will discuss what all these things, but till now just important is to understand the neighborhood overlap concept, that is common friends divided by total number of friends. So in the numerator it will be common friends, that is common neighbors between I and j. If I want to do the neighborhood overlap of I and j node, so that is ni intersection nj, that means common friend between I and j. Okay, common friends or common neighbors between I and j divided by ki minus 1. Ki is the degree of I, kj is the degree of j. So ki minus 1 plus kj minus 1 minus this numerator part, that is the common neighbor. Okay, so that is how you find the neighborhood overlap. Okay, so this is the second formula to know. This is the first formula, clustering coefficient, and this is the second formula that you should remember. And then you have this structure of weak ties. So the structure of weak ties is a theory proposed by that same thing, same researcher Mark Granovetter in 1973, stating that weak social ties play a more crucial role than strong ties in spreading information, opportunity, and innovation across different social groups. Same thing, core idea: strong ties, dense local clusters, that is clique. Okay, and weak ties, bridges connecting different clusters. Thus a weak tie act as a global connector of the network. Okay, so you can see in this diagram, you can see this is one clique and this is another clique or community or anything cluster, you can say. So these are the two cluster, but to join this two cluster we have to have a tie between that, and that tie cannot be strong, because the strong tie will always be inside the clusters or always be inside the clique, but the tie that joins the two cluster, that is always a weak tie. Okay, so this is the weak tie or bridge connecting different clusters. Okay, and strong tie will exist in between the dense local clusters. Okay, so thus weak tie act as a global connector of the network. Okay, so how we can say, what are the feature of differentiation between strong tie and weak tie? Interaction, it is frequent, like this. Here you can say the interaction of the nodes that is between in the dense cluster, that will be frequent, but weak ties, that is infrequent. Only one tie here, but there are many ties over here and there are many strong ties over here also. Okay, emotional closeness high, here low. Strong tie you have high emotional closeness, and here you have low. Trust also high as well as low. Neighborhood overlap high low again. uh, a neighborhood overlap, you can see here you will have more common neighbors, and here also you have more common neighbors, but in between you have less common neighbors, right? So that is why neighborhood overlap, it is high in strong ties and low in weak ties. Network position inside the clusters. Okay, because strong ties you will have inside the clusters, and between the cluster you will have weak ties. Role: local enforcement and global diffusion. So whenever you have this strong ties, you can have more local enforcement. Okay, but for global diffusion of information from one cluster to another cluster, you will have to rely on this weak ties. So this is the differentiation or structure of the weak ties. Okay, and then overlap value, that is nothing but neighborhood overlap. So if the neighborhood overlap is high, okay, so in neighborhood overlap is high when the common neighbors are high, right? So that will be inside the cluster. So inside the cluster, that is why you will have a strong tie. And neighborhood overlap will be low when in between the cluster. So that is why neighborhood overlap value, when it is low, you will have weak tie. And 0, that is local bridge. Okay, so we will discuss what is this local bridge. So let me just admit someone. Yeah. So you have this bridges. Okay, so bridge is nothing but a weak tie, or any type of weak tie is known as bridge. So an edge is a bridge if removing it disconnects the network into two separate components, like this. Okay, so every weak tie is nothing but your bridge, right? So because every bridge is nothing but your weak tie, or we can say reverse also. Like if we remove this weak tie, what will happen is we will have two separate components of network. Okay, so that is why an edge is a bridge if removing it disconnects the network into two separate components. Okay, so edge E is a bridge if G minus E is disconnected. Okay, so that is how we say this. So G is the complete graph, and if we remove this E edge, so what will happen is disconnected graph. So that is known as the definition of bridge. Okay, so this diagram, you can see this. If we remove this edge, what will happen is if we will have two separate components. So this thing is known as the bridge. Okay, this thing is known as the bridge. Now what is a local bridge? An edge is a local bridge if its endpoint have no mutual neighbors. So if the endpoints of this edge does not have any mutual neighbors, so what will happen is it is a local bridge. Okay, so this is the definition of local bridge. In a local bridge, what will happen is this ni, or the common neighbors, will be 0. So when the common neighbors will be 0, what will happen is overlap or neighborhood overlap is 0. So that is why this value is 0, because if this is 0, you can see in the formula, if your numerator, this is 0, your numerator will be 0 and your neighborhood overlap will be 0. So this is known as local bridge. So again I am repeating, an edge is a local bridge if its endpoint have no mutual neighbors. Okay, now the difference between bridge and local bridge, it disconnects the entire graph. Okay, local bridge, it disconnects local neighborhoods. Okay, bridge is rare and local bridge is common. Strong structural role, strong diffusional role. So let's forget this, just focus on this definition. So an edge is a bridge if removing it disconnects the network into two separate components, and edge is a local bridge if its endpoint have no mutual neighbors. So this is the difference between bridge and local bridge. Okay, so let's move on to the another topic known as embeddedness. Embeddedness of an edge measures how deeply the connection is situated inside a local social neighborhood based on how many mutual neighbors the two endpoints share. So very easy, embeddedness is nothing but the common neighbors. Okay, EIJ is nothing but your intersection, that is NI intersection NJ. Okay, so that is nothing but your common neighborhood. So in the overlap formula, the this thing or the numerator is nothing but your embeddedness. Okay, so embeddedness of an edge measures how deeply connection is situated inside a local social neighborhood based on how many mutual neighbors the two endpoints share. It counts how many common friends that two connected people have. So this is an important definition. It counts how many common friends the two connected people have. Okay, now Ni, that is set of neighbors of node I, Nj set of neighbors of Nj, and this is the mutual number of mutual neighbors. Okay, so embeddedness value, if it is high, so what will happen is strong tie, deep social integration. If it is a low, it is weak tie. If it is 0, so what will happen is your overlap value will be 0 and it will be nothing but your local bridge. Okay, so this is embeddedness. So nothing but in your neighborhood overlap formula, the numerator or the mutual neighbors that the two nodes share, that is nothing but known as your embeddedness. Okay, so embeddedness, it counts how many common friends the two connected people have. Okay, so this is a good definition. It counts how many common friends the two connected people have. So this is known as embeddedness. Okay. Now you have this another concept known as this structural whole. Structural whole exists when an individual connects two or more groups that are otherwise disconnected from each other. Okay, so again I am repeating, structural whole exists when an individual connects two or more group that are otherwise disconnected from each other. Structural whole is a gap between two communities, and the person who bridges the gap is known as broker. Okay, so if you say there are two different communities, like you can say this is one community and this is one another community, so the person who bridges the gap between the two communities, that is this node and this node. Okay, so this is known as, these two are known as structural holes. Okay, a structural holes is a gap between two communities, and the person who bridges the gap is known as broker. Okay, so introduction, if A is connected to B and C, and B and C are not connected, then A is bridging a structural hole. Okay, this gives information. This gives A information advantage, control, and influence. Like A is connected to, like this is A. Okay, and this is A is connected to B. This is B, and this is C. Okay, so A is connected to B and A is connected to C. So A is bridging the structural hole between B and C. So this is how we define the structural hole. So this gives A informational advantage because B will always talk to A and C will also give information or share information to A. Now B can have its own social circle X, C can have its own social circle Y. Okay, so this is one community and this is one community. Okay, and A is actually a broker. Okay, a person who bridges the gap is known as broker. Okay, so this a structural hole is a gap between two community, and person A who bridges the gap between the two community is known as broker. Okay, so this A has information advantage, control, as well as influence. So that is how we define the structural hole. Okay. Now, what are the benefits? Informational advantage. This broker will have information advantage, that is early access to novel info. Control advantage, control flow between the two groups. If A blocks the information from this side, then what will happen is the information will not flow. So it has the control advantage. Career advantage, so same thing, better job. Innovation advantage, combining ideas from different groups. Okay, so A has the innovative advantage also, it can combine information from different groups. So that is the concept about structural holes. Okay, so this is another concept. Then we have this social capital. Social capital is the advantage or value a person gains from their position in a social network. Okay, who you know plus where you sit in the network, your power and opportunities. Okay, so that is how we define, like bonding social capital. So social capital can be two types. Bonding social capital, it happens when from your strong ties, dense cluster, high trust, emotional support, example close friends, family, and team members, that are strong ties. Okay, and bridging social capital from weak ties, structural holes, access to new information, example acquaintances and cross department contacts. So this is again a concept. So again I am repeating, social concept is the advantage or value a person gains from the position in a social network. So who you know, that means your neighbors, where you sit in the network, that is your position, that will give you power and opportunity. Okay, so if you are very close to the bridge, what will happen is you will have advantage of this weak ties. Okay, and if you are inside in a dense cluster, what will happen is you will have advantage of your strong ties. So this is known as social capital. So measure of this the social capital, it is measured by centrality measures. So most important is betweenness centrality. Okay, that will give you the brokerage power. Okay, degree centrality, it will give you the popularity. Closeness centrality, speed of the reach. And then you have this eigenvector centrality, that will give you the influence. So what is centrality? We have discussed in some classes also, but let's discuss in detail. So centrality measures in social network. One is this degree centrality. So what is this definition of degree centrality is? Degree centrality, it measures how many direct connection edges a node has. So very simple. How many direct connection a node has, that is nothing but your degree or degree centrality. We also call it as commonly as degree. So it indicates popularity, activity and immediate influence. If it is high, your node is very popular and has many contacts. If it is low, it is isolated or weakly connected. So this is degree centrality. It is given by this definition CDI, that is the degree centrality of this I node, that will be Ki, that is number of neighbors of node I divided by total number of nodes. Okay, so this is a measure, so that is why this value will be in fraction. Normally when we call it as degree, so that will only be Ki. Okay, that is number of neighbors of node I, but this is a centrality measure, so this will be in fraction, so that is Ki by n minus 1. N is the total number of node and Ki is nothing but the number of neighbors of node I. So example, if a student has 10 friends in a class of 50, then its degree centrality will be 10 by 49 or 0.204. Okay, 10 because the number of neighbors of node I, that will be number of neighbors or number of direct connection of node I, that will be 10 because he has 10 friends, and divided by n minus 1. N is the total number of strength in the class, that is 50 minus 1 is 49. So 10 by 49 will be 0.204. So this is one measure, that is degree centrality, that will give you the popularity. Second is betweenness centrality. This is again very important. So what is this betweenness centrality? It measures how often a node lies on the shortest path between other nodes. Okay, so this is betweenness centrality. Okay, so again I am repeating, measures how often a node lies on the shortest path between other nodes. Okay, so if these nodes lie in the shortest path between other nodes, what will happen is this will nothing but your broker. Okay, so interpretation is, if your this betweenness centrality is high, you will have strong broker, bridge or influencer capability, and if it is low, you are a peripheral actor. Okay, so this is how we interpret it. Formula, this is the formula. Okay, CBI, that is the betweenness centrality of node I, that will be given by sigma sigma, that is summation sigma st, that is total number of shortest path between s and t, and sigma sti. Okay, sigma st is this one. Okay, that is total number of shortest path between s and t, and sti is the number of those paths passing through this I node, because we have to know the betweenness centrality of node I. Okay, so node I. So here you can see in the figure they have measured the betweenness centrality of node E. So that is why sigma STE, here we have written I, but here we are measuring for E, that is why sigma STE divided by sigma ST. Sigma ST is nothing but total number of shortest path between S and T, and sigma ST is number of those paths passing through E. Okay, from S to T passing through E. So that is in the numerator, and below in the denominator total number of shortest path between S and T. Okay, so that is how we measure the betweenness centrality. Okay, it indicates brokerage, control and gatekeeping power. Okay, so that is why this is one of the most important centrality, because broker is very important. Broker can either break or make the weak tie, and actually important, very important for important for joining two different communities. So this is a very important measure, betweenness centrality, and betweenness centrality will give you the brokerage power. Okay, so this is the second centrality. Third centrality is the closeness centrality. Closeness, as the name defined, it measures how close a node is to all other nodes in the network. Interpretation, if it is high, fast access to everyone. Low, that is the node is far from others. It indicates speed of information access and the spread. Okay, so formula, this is the formula, n minus 1 sigma j dij. Dij is the shortest distance between the I and j, that we have to do for all nodes, all the part of the dij, and n minus 1. N minus 1 is, n is the total number of node minus 1. So that is closeness centrality. And we have this fourth centrality, that is eigenvector centrality. it measures a node influence based not just on number of connection, but on how influence its neighbors are. Okay, so that is eigenvalue centrality. So it measures nodes influence based on not just number of connection. If it's only on number of connection, that is degree centrality, but on how influential its neighbors are. So degree centrality plus the influence, that will give you the eigenvector centrality. So if it is high, influential plus connected to influentials, and low, it is peripheral. So this is the formula. So I'm not going into the formula. So we will learn about the formula if we discuss this in the class. But this is how you define the eigenvector centrality. Okay, so these are the centrality. Now betweenness measures and graph partitioning. So edge on nodes with high betweenness centrality lie between the community. Okay, that I have told you. Like you have seen this. Like if this E has the highest brokerage power, then it will lie between two communities. Okay, so this is what has been told. Edge on nodes with high betweenness centrality lie between communities. So removing them separate the graph into two meaningful community or partition. So that is known as graph partitioning. Okay, using this betweenness measure. So again I am repeating, edge on nodes with high betweenness centrality, it lies between two community. So if we can remove the edge or node with this edge or node with high betweenness, what will happen is this two community will get separated. Okay, so that is known as graph partitioning or community detection through graph partitioning. Okay, so this is the graph. So you can see all these nodes in all these edges have high betweenness. So if we can remove one edge from all the edges from this, what will happen is we can get different communities. Okay, so this is how we define the graph partitioning. That means separating the network into two or more different communities. So that is graph partitioning. Now why high betweenness edges indicate community boundary? So inside a community many alternative paths exist, so shortest paths are spread out, but between community only few edges connect them. Okay, so almost all the shortest path go through this edges. Okay, so if you have to go from one community to another community, you have to pass through that shortest path. Okay, so only few edges connect them, so almost all shortest path go through those edges. So these edges get very high betweenness. If they get very high betweenness, what we need to do is we need to just indicate the edges which has high betweenness. We have to just remove them, and by that we can do the community detection. So this is community detection. Community detection, process of dividing a network into groups, community or clusters, such that nodes inside a group are densely connected while connections between the group are sparse. Okay, so again I am repeating, community detection, process of dividing a network into groups, community or cluster, these are synonyms, such that nodes inside a group are densely connected. Okay, while connections between the groups are sparse. Okay, so this is the definition of community detection. Now one popular algorithm for this community detection using this betweenness measure is known as Girvan-Newman algorithm. So Girvan-Newman algorithm is a hierarchical divisive algorithm that detect community by iteratively removing edge with the highest betweenness centrality. Okay, so algorithm step, it compute the edge betweenness for all the edges, and then it removes edge with high betweenness, and recompute again, it will recompute the betweenness and repeat until graph split into communities. So that is Girvan-Newman algorithm. Okay, so again I am repeating, it does this using this concept only. Okay, high betweenness. So whenever the edges has high betweenness, if we just remove that high betweenness edge, we will have different communities. So Girvan-Newman algorithm uses this same concept. It is a hierarchical divisive algorithm that detects communities by iteratively removing edges with the highest betweenness centrality. So what are the steps of the algorithm? It compute edge betweenness for all the edges, it remove the edges with high betweenness, it recompute betweenness and repeat until graph splits into communities. So that is how it operates. There is another method known as brute force method by which we do community detection, though it is not recommended because I will say why it is not recommended, because let's say the definition: brute force community detection exhaustively test all the possible partition of the network and select the partition that optimizes a chosen objective function. Okay, so objective function you first choose, and then you will keep on removing the edges one by one, and you see if your objective function is maximized or not. If it is maximized, then you will say this is a community, otherwise it is not a community. So that means you have to keep on removing each and every edge iteratively, or one at a time, and then you have to see if your objective function is maximized or not. Okay, by that you have to decide whether it will form community or not. So it enumerate all the possible ways to divide n nodes into communities, compute quality metric, that is example modularity, for each partition, and choose the best partition. Okay, so advantages: it guarantees global optimal partition, exact method, but the disadvantage is it is computationally infeasible for large network. It can only operate for very small network up to 15 nodes. Okay, so that is why this is not useful at all. We operate with this girvan newman algorithm, not by brute force algorithm, because it is only useful for small networks with nodes less than 15. Otherwise, if his node is greater than 15, what will happen? It is computationally infeasible for larger networks. So that is the brute force method. So these are the two methods for this community detection. Okay, so this is the theory for your class, or summary of this week. So topics on which the assignment question will be based: strength of weak ties, Granovetter's experiment, the neighborhood and neighborhood overlap, structure of weak ties, bridge and local bridge, structural holes and social capital, betweenness measures, and graph partitioning. Okay, so this was the theory, or the summary of theory for your this week. Okay, so let's move on to the important thing, that is your questions. Okay, uh, yeah, I am from Bengal. Any question? Yes, Saito, I am from Bengal. Anything that you want to ask? Okay, no problem. So let's move to the question answer part. So this is the case one: organizational network, weak ties, and structural holes. A large company has employees in several departmental teams. Team members are closely connected, strong ties, but some employees, like Alice, also have many acquaintances in other department, that is weak ties. Consider this network context. So again I am repeating: a large company has employees in several department teams. That means all the department will form a cluster, all different department will form different clusters. Okay, so team members are closely connected. That means persons who are in the same department, they are closely connected and form strong ties. But some employee, like Alice, also have many acquaintances in other departments. So okay, so Alice is actually forming weak ties. So consider this network context, we have to answer the questions. Okay, so theory required for this case one, that is Granovetter's weak tie theory that we have discussed: strong ties, weak ties. Okay, what is the core idea of Granovetter's weak tie theory? That is, weak tie are most important than strong tie for assessing new information and opportunities. Okay, so this is the Granovetter's weak tie concept. And then embeddedness and neighborhood overlap. So strong ties have high embeddedness, many mutual friends, high trust and redundancy. High embeddedness, many common neighbors. It leads to trust, norm enforcement, strong relationships, redundant information. Okay, and then structural holes and brokerage. Okay, structural hole, gap between two communities. Broker, person who connects them. Okay, so again we have discussed this: people who bridge disconnected group, gain power, control, and social capital. Okay, so this is another concept. And then you have this local bridge, an edge that is only link between two groups, that is local bridge. Local bridge, no alternative path, critical for information diffusion, often weak ties. So this is the whole theory. Okay, so this theory is explain how weak ties and brokerage position enable access to novel information, information, innovation, and social capital, while strong ties with high embeddedness create trust, cohesion, but mostly circulate redundant information. So this you all know, we have discussed in the theory. So let's answer one by one. So according to Granovetter's weak theory, which situation in this network is most likely to bring new information like a job opportunity to Alice? Alice's close colleague in the same team shares a tip. Option B, Alice learns of a job opening from close acquaintances in another department. Alice reads about the job in any internal memo posted by HR. Alice's mentor, her team leader, informs her directly. So I hope you know the answer. Guesses for this? This is Granovetter strength of weak ties. So Alice will get job opportunity from weak ties. That is, yeah, B. Yeah. Alice learns of a job opening from close acquaintances in other department. Okay, so this is not true. Alice close colleague in the same team shares a tip. So that might not happen, because if Alice is in the same team as our other department mates, what will happen is they have the same information, they don't have any new information. Okay, so it is most probably that the other team members will not know any new job opportunity. Okay, so Alice reads about the job in an internal memo posted by HR. That is also because it is a same department, so that is also less less likely, and also no HR will share another job opportunity information. So Alice mentor, her team leader, informs her directly. Again, this is close friends or strong tie. So information will be in this. Okay, that is Alice learns a job opening from a college acquaintances in other departments. Okay, so option B is the correct answer. Granovetter weak tie theory argues that weak tie acquaintances connect individual to different social circles, making them more likely to provide novel, non-redundant information. This is important, such as new job opportunity. Close colleagues, mentors, or HR memos usually circulate information already common within Alice's immediate network. So that is the option B is the correct answer. I hope you all got this. Okay, very simple question but very important question. Okay, now let's move on to the next question. In the company network, an edge between two employee has high embeddedness. What does this employ about their relationship? They have many mutual friends, so they trust each other and can enforce norms. They are the only connection between their team, acting as a bridge. They share no common contacts, neighborhood overlap zero. They have completely different roles and no trust. So any guesses for this? Again, an easy question, I guess, because if you know the embeddedness concept, it is very easy. Embeddedness means uh, common neighbors, right? More the embeddedness, more is the common neighbor. So more is the common neighbor, they have many mutual friends. Okay, common neighbors means what? Many mutual friends. Okay, so they trust each other and can enforce norms. So option A is the correct answer. Okay, they are the only connection between their team, acting as a bridge, that we cannot say. They share no common context, so that is absolutely wrong. This is absolutely opposite. Okay, and they have completely different roles and no trust. This is again wrong. Okay, because if you have high embeddedness, you will have more trust. Okay, so option A is the correct answer. So an edge with high embeddedness means two employees share many common neighbors. This leads to trust, repeated interaction, and norm enforcement, but usually less novel information since their contexts overlap heavily. Okay, so option A is the correct answer. Now move on to the question number third. Alice acts as a liaison between the marketing and engineering teams, which are otherwise not directly connected. What network concept describes Alice's advantage in this position? Click formation, community detection, structural hole or brokerage, or D, triadiac closure. This is again very simple, I hope. Any guesses for this? Yeah, see. Very easy. See, structural hole brokerage, right? Because Alice is in the weak tie in between two different communities. Okay, this is one community, this is one community. One community is marketing, one community is engineering team, and Alice is in between. So she has been acting as a structural hole or brokerage. Okay, so that is why option C is the correct answer. So Alice connects two otherwise disconnected group occupying a structural hole. This gives her brokerage advantage, access to diverse information, control over information flow, and increased strategic information in the organization. So option C is the correct answer. Now let's move on to question number 4. In this organizational network, an edge that is only path connecting two distinct groups of employees with no alternate route is called a strong tie, local bridge, cluster edge, embedded tie. In this organizational network, an edge that is only path connecting two distinct group of employees with no alternate route is called a, very easy again, not a strong tie, definitely. Local bridge, yes. Cluster edge, no. And embedded tie, no. So option B is the correct answer. Okay. Okay. So a local bridge is an edge whose removal would disconnect two groups because there is no alternative path between them. Such edges are often weak ties and are crucial for information diffusion across the community. Okay, whereas strong tie will have this local reinforcement. Okay, but not information diffusion between two community. Okay, so that is why option B is the correct answer. Now let's move on to the next one, that is, in this context, which of the following statement about weak ties Alice acquaintances are correct? Okay, so they tend to be bridge between groups and are crucial for information flow. That is true. They usually form redundant parts within a tightly knit community. They provide access to novel information from outside Alice team. They create high clustering close triads in Alice local network. Again, very simple question. So any guesses for this? Which of the following statement about weak ties? So we have to see which of the statement correct about weak ties. This is very easy. So they tend to bridge between groups and are crucial for information flow. That is very true. And they usually form redundant parts? No, because strong ties form redundant part, but weak ties don't form redundant path. So this is false. They provide access to novel information from outside Alice team. Again, it is true. Novel information, whenever we are talking about weak ties, then novel information will be shared between the two different communities. Then they create high clustering close triads in Alice local network. That we cannot see because Alice is a weak tie, not a strong tie. Strong tie, this is true for strong tie. So option A as well as option C is the correct answer. Okay. So weak ties typically span different group acting as a bridge, enabling innovation and information diffusion. They do not increase clustering or redundancy. That is properties of strong ties. So this B as well as this D are property of strong ties, whereas A and C are the properties of weak ties. Okay, so by this we end our first case. Okay, now let's move to the next case, that is friendship triads and clustering. A group of friends at a university form a social network. Okay, some triads, that is triple of students, are fully connected, everyone know everyone, and others are open, that is one friendship missing. We examine how clustered these friendships are. Okay, so let's move to the questions. This is the case second. Okay, so theories for this case: triadiac closure theory. If A is friend with B and B is friend with C, then A and C are likely to become friends. Okay, this explains why closed triad triangles form in social network. Open triad, closed triad, we have discussed. Clustering coefficient, this is the formula of clustering coefficient: 2 into number of links among neighbors, that is 2 into EI divided by ki minus 1. Okay, so this is the formula of this clustering coefficient. High clustering coefficient, tightly knit friend group. Low clustering coefficient is sparse connections. Okay, Neighborhood overlap, this is the formula of neighborhood overlap. We have discussed that is number of common friends of I and j divided by ki minus 1 plus kj minus 1 divided by this same thing, number of common neighbors. Okay, so this is neighborhood overlap. Neighborhood overlap, if it is 0, that is local bridge. High overlap, that is embedded strong tie, connection to tie strength, trust, redundancy, etc. And then we have this local bridge, core idea, an edge that connects two parts of the network without alternative shortest path, that is local bridge. If for the local bridge, your this overlap will be 0, or embeddedness or number of common neighbors between I and j, that will also be 0. Okay, so these are some of the theory behind it, behind your case second. Okay, so let's move on to the question answer, and that is friendship triad, where each person is friends with other two, is called a closed triad, structural hole, local bridge, open triad. Very simple. A friendship triad where each person is friends with other two is known as, this two cannot be true, so I am marking this two out. So it is closed triad or open triad. So what will be the answer? Closed triad or open triad? It is closed triad, because each person is friends with other two. That means it is a closed triad. Okay, so closed triad triangle, option A is the true answer, correct answer. A triad where each person is friend with other two forms a triangle, also known as closed triad. Okay, this phenomenon is known as triadiac closure. Okay, and this represents high clustering and strong social cohesion. Okay, so option A is the correct answer. Now let's move on to question number 7, that is the local clustering coefficient of a student nodes measure how likely the student is to start a rumor. The proportion of student friends who are also mutual friends with each other, the number of weak ties the student has, the number of community the student belongs to. So any guesses for this local clustering coefficient of a student nodes? How likely the student is to start a rumor? That does not mean that. The proportion of student friends who are also mutual friends with each other, that is the right answer. Yeah, so local clustering, it means the proportion of student friend who are also mutual friend with each other, so that is known as local clustering. Local clustering coefficient measures how close a nodes neighbor are to forming a clique. It captures the tendency of friends of a student to be also friends with each other. Okay, so that is known as clustering coefficient. Okay, so this is the concept. Option B is the correct answer for this. And then let's move to question number 8. Is this the first numerical question? If a student Dave has 4 friends, and among those friends among those friends there are 2 friendships connection between them, what is Dave's local clustering coefficient? Okay, so clustering coefficient, we know that is 2 into ei divided by ki minus 1 plus this thing, clustering coefficient ci 2 into ei divided by ki into ki minus 1. That is the formula of this clustering coefficient, that has also been given in the question. 2 into number of realized friend links divided by k into k minus 1 for k friends. Okay, this is the formula is also given to you. So very easy. K value will be 4 here because it is the number of friends. Okay, so k equals to 4. Among those there are 2 friendships, so that is why in the ei will be nothing but 2. Okay, so 2 into ei divided by k into k minus 1. So 2 into number of links among friends, so that is 2 friendship connection. Okay, so that is why ei will be 2. So 2 into 2 divided by k is nothing but your 4 friends, so 4 into 4 minus 1. So 2 into 2, that is 4 divided by 4 into 3 is 12. So 1 by 3 will be your answer. So option B will be your answer. So I hope this is clear to all of you. You have to just see what is the K and what is the EI. EI is number of links among friends. So that is 2 friendship connection has been given. So your EI will be 4. This is nothing but your EI. Okay, that has been according to our formula. That is nothing by EI. Okay, so EI is nothing but your number of links among friends. So that is given as 2. EI is given as 2 and K is nothing but the number of friends. So K is given as 4. So K is 4 and EI is 2. So very easy, 2 into EI divided by K into K minus 1, that will be 4 by 12, that is 1 by 3. So option B is your correct answer. Okay, so this is direct formula question. Just you have to see what are the parameters. Okay, what are the value of the parameters. If you just understand the value of the parameter, it is very simple to calculate the clustering coefficient. Okay, so this is question number 8. Now let's move on to the question number 9. The neighborhood overlap of an edge between two students x and y is defined as the fraction of their friends that they have in common. If x and y share no mutual friend, their neighborhood overlap is 0, and that edge is a local bridge, closed triad, strong tie, embedded tie. So this again, if your neighborhood overlap is 0 or there is no mutual friend between this x and y, what will happen is that the numerator will be 0 in the neighborhood overlap formula, and the neighborhood overlap will be 0. Okay, this is also known as embeddedness, right? That is number of mutual friends. So embeddedness is 0, neighborhood overlap is 0, and that is known as local bridge. Okay, so option A is your correct answer. So if two students share no mutual friends, the edge between them has neighborhood overlap 0. Such an edge often acts as a bridge between otherwise disconnected group, which is the definition of a local bridge. Okay, so option A is the correct answer. Local bridge is the correct answer. Now let's move to the next question, that is to calculate the neighborhood overlap. Yeah, if a student Y shares two mutual friend with student Z, Y has a total degree 5, Z has a total degree 4, the neighborhood overlap is which of the best option? So neighborhood overlap is above is number of mutual connection, that is Ni intersection Nj, that is the numerator, and denominator will be ki minus 1, sorry for writing, ki minus 1 and plus kj minus 1, this is kj minus 1 and plus, sorry, no, minus this ni minus nj. Okay, ni minus, sorry, ni intersection nj. Okay, so this is the formula of your neighborhood overlap. So this is nothing but ni nj, that is given, that is if student Y shares two mutual friends with student Z, so this is given as 2. So numerator is 2, denominator ki, the degree of student Z. Y has total degree 5, so 5 minus 1 is 4. Okay, and plus 4 minus 1 is 3. Okay, and minus 2. So this is your answer. So 2 divided by 5. Okay, so 2 divided by 5, or option D is your right answer. Okay, so this is the whole thing. So again I am repeating here, this is the formula of neighborhood overlap, that is ni intersection nj, this is nj. Okay, ni intersection nj divided by ki minus 1 plus kj minus 1 minus this ni intersection nj. So ni minus intersection nj, that is the mutual friends, that is given, that is 2. So ni intersection nj is 2, ki is given as 5, kj is given as 4. Just put the formula and you will get the answer. Okay, so let me just erase this for better visibility. Okay, yeah, so this is the thing. So very easy. This is the formula, number of common neighbors, that has been given 2 divided by this ki minus 1 or kx, whatever you call it, ki minus 1. So ki is nothing but your 5, kj is nothing but your 4, and number of common neighbors is 2. Just put the value and you will get 2 by 5, that is 0.4 is the answer, or 2 by 5 it has been given. So option D is your answer. So again a direct formula question. Okay, So, are the questions clear? Neighborhood overlap, how to calculate neighborhood overlap, how to calculate the clustering coefficient. Is it clear? Any doubt in
Yes,
this?
sir.
Yeah. Okay, nice. So let's move on to the next case, that is brokerage and community detection. In an organization social network, some employees connect otherwise separate communities. We use community detection Girvan Newman algorithm to identify cluster and consider how brokers and social capital emerge. Okay, so this is the thing, brokerage and community detection. Okay, so let's move on to the theory behind this. Brokerage, structural holes, social capital, we have discussed all this. Girvan Newman algorithm, this also we have discussed. It is based on this edge between the centrality. Okay, between the centrality of edge. So the more will be between the centrality of edge. That edge, if we will remove, what will happen is remove edge with high between the centrality, and then we can get two different communities. Okay, so that is the Girvan Newman algorithm. So this theory is explain how broker gain a strategic advantage by bridging disconnected group, and how network communities can be detected by iteratively removing high betweenness edges to reveal underlying cluster structure. Okay, so this is the thing. We have discussed the theory, so I'm not again going into theory. So let's move on to the question. An employee who connects many colleagues across different departments is likely to have increased social capital by bridging structural holes, network constraint and isolation, clustering coefficient in their local network, closed loop redundancy. So any guesses for this? Very easy again. An employee who connects many colleagues across different departments is likely to have increased option A, right? Social capital by bridging the structural hole. So already structural hole exists. He she will act as a broker, and will bridge the structural hole and gain the social capital. Okay, so option A is the correct answer. An employee who connects otherwise separate department acts as a broker. So according to Burt's theory of structural holes, so yeah, this structural hole theory has been given by Burt. Okay, so just remember the name in case you might have asked. Such position provide information advantage, visibility and control benefits, which together increase the social capital. Okay, so option A is the correct answer. So this is again very easy. Now let's move on to the next question. In the Girvan Newman community detection method, what is removed first to reveal communities? Nodes with highest degree, edges with high betweenness centrality, random edges until cluster form, and D, edges with dense subgroup. So any guesses for this? Edges with high centrality, yeah, edges with high centrality that we have to remove. If we remove this, we will get different communities. So Girvan Newman identify community removing edges that lie on the many shortest part or has high edge betweenness. This edge typically act as a bridge between communities, so removing them separate the clusters. So option B is your correct answer. Now let's move on to the next question. The Girvan-Newman algorithm produces a hierarchy of communities in the form of a single cluster, dendrogram, flat partition, or D, max distances. So any guesses for this? It is dendrogram. Dendrogram is nothing but a tree-like structure. So what will happen is when the first community will first you can say first in the network, and the first local bridge will be divided, you will get two different communities like this and like this. Now in this community also there will be certain communities in between. Okay, so this and this, so this will form a tree like structure. From this you will get more communities from this more community from this, more community from this, more community from this. So this type of tree like structure from this to this. Okay, and from this to this to this, and this to this. So this type of structure is known as tree like structure or known as dendrogram. Okay, so the Girvan Newman algorithm produces a hierarchy of communities in the form of dendrogram. Okay, so this is the first generation, and this is the second generation, this is the third generation, like this. So that is why hierarchy of communities. Okay, so this is known as dendrogram. So as edges progressively removed, the network splits into smaller components. This produces a hierarchical tree of division called as dendrogram, showing community structure at multiple scales. So option B is the correct answer. Okay. So question number 13. Uh, Correct answer is option B. Now let's move to question number 14. If Alice is a broker between two community, what risk does she face according to social network theory? Increased time energy to maintain ties, trade-off, automatic promotion to a managerial position, losing all her intra-community ties, having a zero clustering coefficient. So any guesses for this? So it will be option A. Yeah. So what will happen is brokers benefits from access to diverse information, but face maintenance cost. Okay, they must invest time and effort to sustain ties across multiple communities. This is classical brokerage trade-off in the social network theory. So option A is the correct answer. Automatic promotion, managerial post, this does not have any significance. Losing all her intra-community ties, this is not right. It is not true that Alice will lose all her intra-community ties. She will have some ties within her department. Okay, not she will not lose all her intra-community ties. She will have some of the inter-community tie also. Having a zero clustering coefficient, that also we cannot say true, because this is not true. Okay, so option C is not true. So she can have some structure, some clustering coefficient. Okay, so option C, D is not true. Option B cannot be true, and option A is true for this. Okay, so this is a different type of question. So just remember this, that a broker between two communities have the risk of this brokerage trade-off, that is maintenance cost. They must invest time and effort to sustain tie across multiple communities. Okay, so option A is the correct answer for this. Now let's move on to the next question. Using Girvan Newman algorithm on network with 20 employees, which approach does it use to determine community split? Checking all possible division, that is brute force, removing the lowest weight edge first, iteratively removing edge with high between group communication, merging individuals into growing clusters until modularity peaks. So this will be nothing but your option C. Yeah. Option C is the correct answer. Okay, someone is joining. So option C is the correct answer. Checking all possible division, that is brute force, is not true, because brute force we use for extremely small network, that is with node less than 15. Okay, after that we do not use it because it is highly computationally expensive. That is why we do not use brute force method after 15 nodes. Okay, not even 15 nodes. I think 10 nodes is okay with brute force. Okay, after 15 we do not use this brute force method for community detection. We use this Girvan Newman method that lies on this highest betweenness measure of the edge. Okay, we compute all the betweenness, all the edge betweenness of all the edges, and then we see which edge has high betweenness value, and we remove that edge. By this we do the community detection. So option C is the correct answer over here. So iteratively removing edges with the highest betweenness group communication, the algorithm reluctates edge betweenness after each removal, continues removing the most between community edges. Communities emerged as this high traffic edges are eliminated. So option C is the correct answer. Now we move to the next case, that is the case 4, right? So mobile phone data and Tyson researcher analyze mobile phone call recording among city resident. Higher call frequencies indicate a stronger tie. They check if Granovetter's hypothesis holds. Do people who share many contacts talk more often? Okay. So let's move on to the theories required for this case 4, that is mobile phone data and tie strength. So you will have this Granovetter's core idea, that is weak tie more important than strong ties for spreading new information and connecting different social groups. Okay, we have discussed all this: strong tie, high call frequency, high neighborhood overlap embedded within the clusters, redundant information, high trust, weak ties, low call frequency, low zero overlap, act as bridge, novel information, high diffusion reach. Okay, we have discussed this. Then tie strength, embeddedness, and neighborhood overlap. Again, we have discussed this. The tie strength correlates with neighborhood overlap. This is the formula of neighborhood overlap. Embeddedness is nothing but the mutual neighbors or the common neighbors. Okay, that is embeddedness. And then weak ties as bridges between the cluster, that also we have seen again and again. So this theory explains how strong ties corresponds to frequent communication and high overlap, while weak ties, despite low interaction, play a critical role in bridging communities and enabling large scale information diffusion. Okay, so this is for case 4. Now let's move on to the question part for this case 4. In the mobile phone network, if two users share a large number of common contacts, that is high neighborhood overlap, what does Granovetter's hypothesis predict about their call frequency? They will have a very low call frequency. They will likely to have a high call frequency. Neighborhood overlap has no relation to call frequency. They will only communicate through intermediaries. So any guesses for this? Very easy. So if two users share a large number of common contacts, then what will happen? They will likely have a high call frequency. Yeah, very right. They will likely have a high call frequency. Okay, they will have a low call frequency. This is not right. This is true for weak ties, but it is a strong tie, so this is not correct. Neighborhood overlap has no relation to call frequency. This is false. But more will be the neighborhood overlap. More will be the, you can say, the clustering coefficient of the cluster. So they will have more call frequency, and then they will only communicate through intermediaries. This is also not true. This is also uh, false. This is true for this weak ties, not strong ties. Here we are talking about strong ties, so this will be option B will be your answer. Okay, so Granovetter hypothesis predict a positive relationship between tie strength and neighborhood overlap. If two users share many common contacts, their tie is embedded in a dense social circle, which is typically reflected by frequent communication. So option B is the correct answer. Now let's move to the question number 17. Empirical findings from the mobile data suggest that edges with high weight, many calls, tends to have high overlap, that is many mutual contacts, zero overlap, no mutual contacts, always local bridges, or B, randomly distributed regardless of overlap. This is again very simple, that is A, right? High overlap, that is many mutual contacts. So empirical studies of mobile call records show that strong ties or high call volume usually exist within tightly knit groups where individuals share many mutual contacts, hence strong ties are highly embedded. Okay, so option A is the correct answer. Now let's move on to the question number 18. If the call network in the call network, what kind of tie based on overlap is expected to connect two loosely connected clusters of individual? A strong tie with high overlap, no. A weak tie with non-zero overlap, a repeated strong triadiac tie, a triadiac closer H. So guesses for this? Very simple. Option B, right? A weak tie with near zero overlap. Okay, because we are talking about two loosely connected clusters, so that means a weak tie will form. Okay, strong tie will not form. Strong tie with high overlap, this is not right. And this two characteristic, that is triadiac closure and repeated triadiac tie, these are characteristics of strong ties. Okay, so option C and D is not correct. Option A is not correct. Option B is the correct answer. Connection between different cluster are typically weak ties with little or no neighborhood overlap. These ties act as bridge, enabling information to flow between otherwise separated social groups. So option B is the correct answer over here. Okay, very simple. Now let's move to the next question. If two city residents have an overlap ratio, which statement is true? Oj equals to 0.5 in their call network. Okay, they share all their contacts in common. They have half of their respective contacts in common, suggesting a fairly strong tie. They share no contacts in common. They do not communicate by phone. So, any guesses for this? If two city residents have overlap ratio 0.5, they share all contact in common. That is not correct. They share half of their respective contacts in common. This is true, right? They share no contacts in common. Again, if no contact in common, then your overlap will be 0. They do not communicate by phone. This is again not correct, because 0.5 is there, so definitely they communicate by phone. And they have mutual neighbors, so they have half of their respective contacts in common. So option B is the most likely correct answer. Yeah, they have half of their respective contacts in common, and overlap 0.5 means 50% of neighbors are mutual. Okay, indicating moderate to high embeddedness and relatively strong social tie. Okay, so option B is the correct answer. Now let's move on to the next question. Researchers found confirming Granovetter's theory in mobile data indicates which of the following about weak ties in the network. Weak ties were associated with high embeddedness. Weak ties tend to span between different clusters. Strong ties were never present. Weak ties had no role in information diffusion. Any guesses for this? Very easy, right? Weak ties were associated with high embeddedness. This is not true. Strong ties is only associated with high embeddedness, so this is false. Weak ties tends to span between different clusters, so definitely weak ties will span between different clusters, right? So this is right. Strong ties were never present, so this is again false. Weak ties had no role in information diffusion. So weak ties has the strongest role in information diffusion, but they have weakest role in local reinforcement. Okay, so option D is also wrong. So option B is the correct answer. So weak ties tended to span between different clusters. Confirmation of Granovetter theory in mobile data shows weak ties, despite lower interaction frequency, are crucial for linking different communities and enabling information diffusion across the network. So option B is the correct answer. Now let's move on to the case 5, that is brute force versus Girvan Newman community detection. A network of analysts is clustered into communities. Two approaches are considered: exhaustively testing all the possible splits, that is brute force, versus using Girvan Newman algorithm. Answer question comparing these methods. Okay, so theories that are required for this: community detection. What is community detection? Then community detection by brute force and community detection by the Girvan Newman algorithm. We have discussed again, so let's not again discuss this. So this includes understanding of computational functionality of brute force method, divisive hierarchical clustering process of Girvan Newman, and a concept of dendrogram for hierarchical community structures. Okay, so all these things, so just move to the question answer and it will be much clear. A brute force community detection method iteratively removes edges by centrality, tries every possible division of nodes into groups, merges nodes based on degree, uses edge overlap matrix only. So any guesses for this? Very easy. Brute force. Brute force means it tries every possible division of nodes into groups. Okay, and based on the maximization of the objective function, it can be modularity. It forms the community. Okay, so brute force method enumerate all possible partition of nodes, evaluate each one using a chosen objective function. This guarantees completeness but is impractical for large networks. So it is impractical for nodes greater than 15. Okay, 1 5. So this is the brute force community detection method. So option B is the correct answer. Okay. Now let's move on to the next question. The main drawback of brute force method compared to Girvan-Newman is they cannot find the optimal solution. They run too quickly for large network. They are computationally expensive, exponential time. They ignore the edge weight. So again, very easy. They are computationally expensive, right? So that is why we do not use brute force method for large networks or any networks greater than practically any networks greater than 15 nodes. Okay, so option C is the correct answer. The number of possible partition grows exponentially with network size, making brute force approach infeasible beyond very small graphs. So option C is the correct answer. Girvan-Newman differs from brute force in that it seeks community by maximizing the local clustering coefficient, recursively removes likely inter-community edges, randomly assign nodes to communities, require prior knowledge of number of communities. So any guesses for this? It recursively removes the likely inter-community edges, right? Yeah. So it recursively removes the likely inter-community edges. Okay, that is Girvan-Newman method. So based on the edge centrality or edge betweenness centrality, it removes the edges that has high edge betweenness centrality, and by removing that you will get two different communities. Okay, so that is how it operates. So Girvan-Newman is a divisive heuristic. It repeatedly removes edges with high betweenness centrality, which are likely to lie between communities rather than testing all the partitions. So option B is the correct answer. Question number 24. In a small network, both brute force and Girvan-Newman find two communities of equal size. What advantage might Girvan-Newman have? It guarantees the globally best partition. It is easier to explain by edge betweenness concept. It provides a clear hierarchy dendrogram. It avoids calculating any centrality measures. So any guesses for this? So according to me, it can be B as well as C. So let's see. It is only given C. So easier to explain by betweenness concept. So according to me, B can also be correct answer. But okay, B as well as C is the correct answer. So it provides a clear hierarchical dendrogram. Even when both methods find the same final split, Girvan-Newman, it is a dendrogram revealing community structure at multiple resolution, which brute force does not naturally provide. Okay, so that is the thing, because it just removes one edge, forms two different communities, and it forms a hierarchical division. Okay, so this is one advantage of Girvan-Newman method. Okay, but according to me, B can also be correct answer. Okay, B as well as C according to me, but C is given over here, so C is most correct. Okay, provides a clear hierarchical dendrogram. Now let's move on to the next question. Which statement is true about this two community direction approach? Brute force always yields fewer community than Girvan-Newman. Girvan-Newman cannot handle weighted networks. Brute force exhaustively finds the best split by any criterion, example inter edge ratio. Girvan-Newman is also a brute force in computing betweenness. So this is actually not correct. Girvan-Newman cannot handle weighted networks. This is false. Most of the networks are weighted only. Brute force always is fewer community than Girvan-Newman. This is also false. So option C is the correct answer. Okay, yeah, brute force exhaustively finds the best split by any criterion. Brute force method can guarantee optimally with respect to choose an objective function, because they examine all possible partitions. Girvan-Newman is heuristic and does not guarantee a global optimum. Okay, so option C is the correct answer. Okay, so again I'm repeating, brute force method can guarantee optimally with respect to a chosen objective, because they examine all possible partitions. Girvan-Newman is heuristic and does not guarantee global optimum. Okay, because brute force it will give you a guarantee optimal, but the problem is it is very highly computationally expensive. So that is why we go with Girvan Newman only. Okay, so option C is the correct answer over here. Now let's move on to the last case, that is local bridge and rumor spread in a tightly knit school. Rumor spread through friendship network. Most students are in dense clique, high embeddedness, but a few friendship act as local bridge between the cliques. We analyze how this affects rumor spread. Okay, so theory is required. Granovetter's weak tie theory, local bridge, embeddedness and neighborhood overlap, and information rumor diffusion. So core idea, network structure determines how far and fast information spread. Our student must know dense clique, fast internal diffusion, bridges enables cross clique diffusion. Diffusion is nothing but the flow of information. Okay, weak ties essential for global spreading. Okay, so this theory explains how rumors circulate rapidly inside dense cliques but rely on weak ties and local bridges to spread across different social group, that is across the communities or cluster, making bridges critical for large scale diffusion. Okay, so this is the thing. So let's move on to the question part. Local bridge in this network is an edge with endpoints, high neighborhood overlap, many mutual friends, no mutual friends, neighborhood overlap 0, maximum between the centrality or D being reinforced by multiple interaction. So this you all know, local bridge means no mutual friends, that is neighborhood overlap is 0. So that is the characteristics of local bridge. Okay, so option B is the correct answer. Local bridge is an edge whose endpoints share no common neighbors. Removing it increases the shortest path distance between the two nodes, often disconnecting the clique. So option B is the correct answer. Now let's move on question number 27. In terms of rumor propagation, edges with high embeddedness, many mutual neighbors, tend to quickly spread the rumors to new part of the network, keep the rumor circulating within a local clique, stop the rumor entirely, always become local bridge. So it is high embeddedness. High embeddedness means strong ties. Strong ties means it will the information will be inside the cluster only. So it keeps the rumor circulating within the local clique or the cluster. Okay, so option B is the correct answer. So edges with high embeddedness lie inside the dense group. They promote redundant transmission of information within the clique but contribute little to the spreading the rumor to new part of the network. So option B is the correct answer for question number 27. Okay, so let's move on to question number 28. Which statement about rumors and weak ties is supported by network theory? Rumors spread faster along the edge with many mutual friends. Bridges weak ties, so we have to consider for weak ties. Okay, bridges weak ties help the rumor jump between the cliques. Only strong ties carry rumors in a dense network. Rumors cannot cross a local bridge. So any guesses for this? Option B, right? Bridges, weak ties help the humor jump between the cluster or cliques. Okay, rumors spread faster along the edges with many mutual friends. Yeah, this can be true, but this is only for within the cluster. If we are talking about the whole network, this is not true. Okay, so this is true. Only strong ties carry rumors in a dense network. Only strong ties carry rumors in a dense network. So strong ties, weak ties can also carry in a dense network. Yeah, this can be correct. Okay, rumors cannot cross a local. This is absolutely wrong. So A and C can be partially correct, but actually B is the most correct according to me. Yeah. So bridges, weak ties help the rumors jump the cliques. Network theory shows that weak ties, especially local bridge, connect different cliques. These ties are crucial for allowing rumors on formation to cross the community boundaries. So option B is the most appropriate answer. Question number 29. If student X has a friendship that is local bridge to another cluster, X is likely highly embedded in their own clique and also well connected to other clique. We cannot say this having no influence or rumor spread. The sole connection point for rumor to reach the other cluster. Okay, so as it is a local bridge, So this is correct. Okay, this is the sole connection point for a rumor to reach the other cluster, because it is the local bridge. If it is a weak tie, then we cannot say only connection, but as it is a local bridge, then it is the only connection, part of a complete triad with other clusters. So part of complete triad with other, this is also false. Okay, so option C is the correct answer for this. Yeah, the if X friendship is a local bridge, then X occupy the broker position. Rumors can reach the other cluster only through X, giving X strategic importance in diffusion. Okay, so question number 29 answer is correct answer is option C. Okay, the sole connection point for the rumor to reach the other cluster is your X. Okay, now last question. When a rumor starts in a dense clique, which tie is most critical for spreading it outside the clique? Any strong tie within the clique spreading outside the tie, that means weak tie, right? Weak tie, that is local bridge to another clique. The tie with the highest clustering coefficient, this is also characteristic of strong tie. This is strong tie. We have to find the spreading it outside the clique, that means weak tie, randomly chosen tie. So this is the correct answer. Weak tie, that is local bridge to another clique. So option B is the correct answer. Why strong ties spread rumors quickly within a clique? It is weak tie acting as local bridge that allows the rumor to escape the clique and propagate across wider network. So option B is the correct answer for your question number 30. Okay, so this is the completion of your question and answer part. Okay, and this links I have given, let me again share this. So this is the link of the YouTube where I will for each class I will upload the recording. This is the link of the drive where you will find both the slides as well as the codes. Okay, and this is the master link where you will find where you can find the recording as well as the drive link. Okay, so third is the master link. So these three links are very important. I have again shared. First is the YouTube link or YouTube channel link where I will be uploading all the videos for all the class. After completion of each class, I will upload the recording of the class. This is the second link, that is the drive link where you can find the slides, each week slide, as well as this codes that I have made for you. And last link is the master link where you can find the first two. Okay, so these are the three links that is important for your session. Okay, so before completing the class, let me just show the codes, so it will be interesting for you. Okay, codes might not come directly in your exam, but it is actually interesting. It will be actually interesting to you. Okay, so yeah, yeah, so these are the two codes. There are community detection with brute force and community detection using girvan newman. Okay, so let me open this. It is community detection using the brute force method. Yeah, so is it visible whatever I am showing you? Is it visible?
Yes, sir.
Okay, nice. So this is the code for community detection using brute force. So I have used the Jacari Karate Club network dataset. So in network X, you can directly load the dataset. You need not to download the dataset from anywhere else. You can load the dataset with one line of code. This is the line of code in network X. You can load this dataset directly without no need to download it. Network X has this inbuilt network. Okay, so first we are just importing the libraries, then we are loading the dataset, and now I have told you that this community detection using brute force, that is actually can be done is only effective for small networks with nodes less than 15. So that is why I have taken only 14 nodes. Okay, after 15 nodes it is computationally expensive, so that is why I have done it for only 14 nodes. The Jacari Karate Club, I think it has 34 nodes or 35 nodes, but 35 nodes it will be computationally very much expensive. That is why I have done with only 14 number of nodes. Okay, and then number of nodes print and number of edges print. So whenever I have print the number of nodes, that is 14 I have taken. Actually it has I think 34. We'll see in the next code, but we have only taken 14 because we have to do it by brute force method. Okay, and the number of edges it has 28 edges, and this is the graph. Okay, so this is the thing, visualize the network. This is how we have visualized the network. Okay, 14 nodes, you can see 1 2 3 4 5 6 7 8 9 10 11 12 13, because it has started with a 0, so that is why 0 to 13. So 14 number of nodes, and all these edges you can see 28 edges are there. And then what we will do, we will do the community detection using brute force method. All the theory has been given here. So what we will do, we will be doing on the basis of modularity. So we will compute modularity. You can just see the code. You can see the code one by one. All the steps has been given, but this is how we visualize with the brute force method. When we have done with the brute force method, this is one community. The green color nodes is one community, and the red color node is another community. So this is our community 1, 0 4 5 6 10 and 11, and this red color is our community 2. Okay, so that is how we have done with the brute force method. And our modularity, this is the best modularity with which our community has been detected. That means first what this algorithm is done, it has tried with each and every possible node and forming a community out of it and calculate the modularity. The best modularity it is getting is this. So for this best modularity, these are the two communities that it will have. Okay, so this is nothing but your brute force method. Okay, so this is first code. Okay, and second code is this one, that is community detection using using this girvan newman. So this also you can see, this I have done for complete Jacari network club. Okay, this I had Jacari karate club. It has 34 nodes. There I have only used 14 nodes because your brute force method is computationally expensive, so that is why we do it for less than 15 nodes. But here I have done it for girvan newman. I have done it for complete 34 nodes of the Jacari karate club. Okay, so again I have just loaded the network, and then this is the number of nodes and edges I have printed. I have do the network visualization. This is the complete theory of Girvan-Newman algorithm, and then what I have done, I have applied the Girvan-Newman algorithm. Okay, so again this is very easy. So you can just uh, with this line of code you can do the community detection. Okay, just you can see. And then what I have done, once I have done the two-way split or first generation split, this is known as first generation split, only two way. And after this two way, what I have done, I have done this multi-level community split. Okay, and then visualize this. So this is our 34 node Jacari karate club. Okay, 0 to 33 you can see, 0 to 33 you can see. So 34 nodes, so that is why 0 to 33, and number of edges it has 78. Okay, and then by Girvan Newman community, I have done it in two-way split. Okay, so this red color is one community and this green color is another community. This is the first level, and then I have done the level 2, level 3 community split. So this is the level 2 split. Okay, this is the level 3 split, and this is the okay, this is the 2 community split. Okay, just we have seen this. This is the 3 community split. Okay, this green color is the third community, and this is the 4 community split. Orange, green, this blue, and this pink. Okay, so this is the third community split. So that is I have done by Girvan Newman method. Okay, so Girvan Newman method is less expensive, so you can do this hierarchy level community split. But brute force is computationally expensive, so you can just do with 2 community only. Okay, so these are the 2 community detection codes. Okay, so everyone, I will request you to just Open this code. When you will open this code, there will be something written over there. Copy to drive. Just copy the code to drive and just run the code. It will be interesting to you. Okay. And also you can change the parameters. You can accept 34. You can just do with 25. Okay. That also you can do it. Okay. 25 nodes, how is the community, and all this you can just visualize it. It will be interesting. So this is all about today's class. Okay, so by this I am ending the session for today. Okay, I hope it is somewhat useful. Okay, and we will meet on the next Tuesday same time, that is 6 to 8 p.m. Okay, so that,
Sir, I have a doubt.
yes please.
Sir, where do we find the previous year question papers for social networks?
Previous year question papers, I don't know, is there something previous year question paper is there or not. All the assignment problems that I am solving, that is assignments of previous year only. Okay.
Okay, sir.
Yeah.
So, is it okay if we study the assignment questions and the one that you're teaching?
Yeah, that will be sufficient. If you, the main thing is if you got the concept or not. If you got the concept, every question you can do. Okay.
Yes, okay, thank
Yeah,
you, sir.
and I think most of the question of this social network is theoretical question. So once you understand the theory, you can just mark it. It will not
Okay.
be that hard. Okay.
Sir, will we have coding questions?
Coding question directly you don't have coding question, but indirectly like this algorithm and all that they can ask it, like brute force versus this girvan newman, right? So you have this
Yes.
one case, right? So that type of cases they can ask, that which
Okay.
algorithm is computationally expensive,
Okay,
which you
sir.
should operate, this is the number of nodes, they will give you 30 nodes, then tell whether you will apply girvan newman or brute force. So you have to tell it, we will go with girvan newman. Okay, like that.
Okay, sir.
This type of question might come, the direct coding question won't come. Okay.
Okay, sir.
Okay.
Thank you, sir.
So by this I am ending the session for today. We will meet the on the next Tuesday same time, 6 to 8 p.m. Okay.
Thank you, sir.
Okay.